Welcome. Let us try and define the symmetry of a given property in a crystal. So, how do we do that? We know that properties are basically things which connect a stimuli to a response, right. So, that is how we define. So, you have a response and the response is due to a stimuli. What connects this response and stimuli is basically a physical property, right. So, this is how we defined physical property. So, and we said that the response and stimuli could be field tensors and physical property is basically a material property tensor. As an example, we considered setting up a concentration gradient which will lead to a flux, and the property which connected them was basically the diffusivity tensor. Okay. So, to define the symmetry of a physical property, there are two things, two ways one can think about. So, let us think about one way. Let us say that I consider a crystal, okay, and I call this as the x axis, this as the y axis, this as the z axis. Now, there are two ways to think about. I can take the same crystal and then I can do a 90-degree rotation on this about a point that is through the center of this cube, for example. What would that do? That would lead me to So, the 90-degree rotation will take x here, and from y it will take from here, and z it will take from here to here. So, now I still have the crystal in the same way as before, right. I have not changed the crystal, I just rotated the axis by which I call these three. Okay. Now, so what happens? My x has become my y has become my x, and my minus x has become my y, and my z, if this is about z that I did, the z was not changing at all. So, that is the same z that I am considering. So, there are two ways to think about. One, you can think of this and then do the operations and then do the symmetry operation and then do everything here, that is one way. Or you can say that I had the same crystal, I said that this is x, this is y, this is z, but somebody else decided to call this as x and that as y and this as z. Okay. In either case, what we are doing is that we are doing a coordinate transformation. Suppose, consider that I am having basically the same crystal, right. I have the same crystal and I decided to call this as the x axis, and then I set up a gradient along this axis and I measured the flux along this axis. So, that was my Jx. So, I will get the diffusivity connecting them, that is basically dxx. But if suppose somebody was calling this as x, okay, in my definition that would have become dyy, but because that person is calling this as x, and so that would be the same as my dxx, because by symmetry if I had done that operation, I have made this x to go here as x and this y to go here and then the z remains the same, then I should not see any change. So, that means dxx and dyy should be the same if the crystal has cubic symmetry. In the similar fashion, if suppose I was looking at the dxy component, I would call it as dxy, but somebody who is thinking that this is x and this is y would get to along x axis. So, the sign x has become y, but y has become minus x. So, they will find that this property is minus d y and x. If suppose D is a symmetric tensor, how did we define symmetric tensor? A second ranked symmetric tensor is Dij is equal to Dji. If diffusivity is a second ranked tensor and it is a symmetric second ranked tensor, then dxy should be equal to dyx, it cannot be equal to, so by symmetry then this is minus dxy, So, dxy cannot be equal to minus dxy. So, that means dxy is equal to 0. In other words, in 2 dimensions, then what has happened is that the diffusivity tensor has become some dx 0 0. So, this can be represented as dx multiplying, and this can be represented using the delta operator. So, in other words, we have shown that in a cubic crystal, so you can extend this argument to z axis also, and so we are doing it for the xy plane, you can do it for the xz plane and yz plane. Same argument can be carried over to show that finally the diffusivity in a cubic system becomes just this d delta ij. Okay. So, which means 1 1 it will have non-zero value, 2 2 3 3 it will have non-zero value, but it will have the same value. So, the matrix, if you look at it, is right, or d multiplying the I matrix, the identity matrix, 3-dimensional identity matrix. So, that means, right, so this is a second rank tensor, now this d is a scalar. So, that means in a cubic system, the second rank tensor, namely diffusivity, has become isotropic, right, because delta ij, this I, the identity matrix, is basically any operation that you do is going to remain the same. So, nothing is going to happen to it. So, that means we have proved that for a cubic crystal, the second rank tensor will be isotropic. So, now isotropy includes the cubic symmetry. What is the point group symmetry of my crystal structure? So, that is cubic. Now, cubic is already included in the isotropy, because isotropy is a much larger symmetry than cubic, and this is how we understand the meaning of symmetry of a physical property. So, what do we mean by symmetry of a physical property? You can think of 2 ways. One, you can think of taking the stimuli and taking the response and in a given crystal, and then do a symmetry operation on the crystal with respect to the fixed frame of reference. You measure these quantities in the same direction, because that is a symmetry operation, you should not see any difference, and that gives you, and in that process, if the property remains unchanged, then that property has that symmetry. But one can also see that instead of doing the operation on the crystal, you might as well do the operation on the stimuli and response themselves, right. You can put it along x and measure along x or y, or you can put it along y and measure along y or x, and these two should be equivalent, because x and y are not distinguished in a cubic crystal, x, y, z, they are all the same, it is just the labeling. In which case, if you do that, if you do the symmetry operation on the stimuli and response, and if you find that the property does not change, and because these are symmetry operations, the property should not change. I mean, if I have this crystal and if I did a 90-degree rotation, that is a symmetry operation. So, nothing changes about the crystal, then the property should not change. So, if I use that demand, then I already see that I end up with the case where the second rank tensor happens to be isotropic. So, all second rank tensors in a cubic system are isotropic, and this is what Neumann's principle also says, because it says that the property of the system should include the point group symmetry. So, isotropy already includes the symmetry that is associated with cubic, so it is okay. So, it can, in other words, the property can have a symmetry which is higher than that of the point group, but the minimum that it should have is the point group symmetry itself. For example, you cannot take a cubic system and find a symmetry which is in such a way that it would distinguish one of the axes from the other two. So, that is a tetragonal symmetry which is lower than cubic symmetry. Cubic does not distinguish between the A, B, C directions, whereas tetragonal distinguishes the C direction from A and B. Between A and B it does not distinguish, but it certainly distinguishes the A and B directions from the C direction, because of which it is a lower symmetry. So, any property in a cubic system will have either cubic symmetry or higher, isotropy happens to be higher than that. because isotropy does not distinguish between any direction. But the property cannot have a symmetry which is lower than the point group symmetry. So, basically the lower bound on what the properties symmetry should be is decided by the point group symmetry. So, this is the meaning of Neumann's principle, and like we showed, the case of second rank tensors in cubic crystals is a very good example, because all the second rank tensors in cubic crystals are isotropic. They do not distinguish between x, y, z directions, and in fact they do not distinguish between any direction. So, that is the meaning of isotropy. If you do not distinguish only between A, B, C, then you can say that it is cubic. So, that is the symmetry of the point group, and the property has a symmetry which is higher than that. It does not distinguish any of the directions. There is one more way to understand this or argue this out, which is based on what is known as representation quadric. In the next part of this lecture, we will look at what a representation quadric is and what it tells about the symmetry in a cubic system, for example. Thank you.